Studies have proved that vaccines lower our chance of getting sick. But what if some people cannot be vaccinated due to other health reasons? To prevent an outbreak, what percentage of people do we need to vaccinate? Is it 70%, 90%, 50%? And does the magic number stay the same? Or does it shift? Instead of guessing, let's use a computer model to simulate an outbreak and find out what it takes to protect a population. Hi, this is Ling from 3D Science Modeling. I'm a science educator and a researcher. I use computer models to help students learn science. Let's dive in. To see how diseases spread, we use a classic computational model including 3 types of people: susceptible, infected, and recovered, short for the SIR model. Here, green people are susceptible. They can be affected. Orange people are affected. They have been affected and can actively pass the disease to the susceptible people. Blue people are recovered. They've recovered from the disease and are now immune. We can watch what happens when just one affected person enters the population and track the outbreak through both real-time graphics and exact numerical data. For example, let's set the population density to 3 people per square unit, giving us 328 people in total. If we introduce one affected person and run the model, the outbreak lasts 60 days, peaking at 183 sick people and resulting in 35 deaths. If we run it again with the exact same setting, notice how the results shift slightly. That's because people in this model move randomly, and transmission relies on probability. Now let's bump the population density up to 8 people per square unit. Unsurprisingly, more people get sick and die. Here's the best part: you are in control. We can adjust variables like transmission rate and vaccination rate to test different scenarios. Let's use our computer model to set up experiments investigating how vaccination impacts an outbreak. Every good experiment needs an independent variable, the factor we can actively change. Here, that's our vaccination rate, or the percentage of the population that is vaccinated. To see the full picture, we'll test rates from 0% all the way to 100%, increasing by 10% intervals. What about other factors, like population density and transmission rate? For this experiment, we'll keep those constant. In science, we call them controlled variables. Now let's consider the dependent variables, the experimental outcomes we want to record. Look at the output monitors on screen. We can track at least 4 key outcomes: outbreak duration, recovered individuals, maximum daily cases, and total death. You can record all of them, or pick 2 outcomes you are most interested in tracking. These will serve as your dependent variables. Now you can create a table in your notebook to record data, or click the link below the video to grab our pre-made Google Sheet template. Remember, to simulate the real world, randomness and probabilities are built into this model. Running the exact same setup multiple times will give slightly different results. To get reliable data, we will run 5 trials for every vaccination setting and then calculate the average. Once you finish data collection, graph the results to reveal the hidden patterns. Here are some sample data and how to graph them in Google Sheet. Simply choose the independent variable and one dependent variable. Insert the chart. See, your data have been graphed. You want to choose aggregate for the independent variable, and then choose average for the dependent variable. Now, the pattern is much more clear. Here are examples of what your graphed data might look like. Notice two major patterns. As the vaccination rate increases, infections and deaths decrease, but the outbreak duration may increase. Once vaccination hits a critical tipping point, disease transmission drops off dramatically and duration also becomes shorter. This tipping point is when we achieve herd immunity, meaning we have enough immune individuals in the population to shield everyone else. The minimum percentage required to reach this protection is called the herd immunity threshold. This activity engages students in 4 NGSS science practices: using a model, planning and carry out investigations, analyzing and interpreting data, and using mathematical thinking. In next video, we are going to discuss if and how the herd immunity threshold change in different situations. If you found this video helpful, please like and subscribe. Share it with more people. Thanks for watching.